Okay, then why don't we get started today? Hi, everyone. Welcome to another episode of Yugabyte DB Friday Tech Talk. Happy Friday to you all. I'm Kannan Muthukkaruppan, one of the co-founders at Yugabyte, and it's my pleasure to welcome Chris Smith today. And today's topic for the talk for engineers by engineers is the math behind high availability and resilience. But first off, I'd like for Chris to introduce himself, and also kind of talk about what got him thinking about this topic. I know you did a blog on this, and it's great to have you cover this on this Tech Talk. So, would love to understand like what got you thinking about this in the first place. So over to you, Chris. Why don't you start with an introduction?
Yeah, that sounds good. Yeah, perfect. And my name is Chris Smith, based over here in the UK. I've been part of the Yugabyte team for 4.5, coming up to 5 years now. Worked in various different database companies along the way, and actually studied maths. So by background, I'm a kind of mathematician. That's what I studied at university. And it was kind of interesting. We were talking with a customer, and they were asking about the kind of resilience and high availability profile of Yugabyte. And we found that we were answering in sort of qualitative terms. We were saying that it was very resilient or highly resilient. We were talking about the RF3 replication factor, which we'll talk about in a minute. And then we found ourselves talking about RF5, and we said, well, that's more resilient, And the customer was kind of struggling to sort of really quantify that in terms of availability and uptime and things like that. So that's what sparked this piece of work, where we decided to look at the maths, as I would say, or the math, as Americans would say, but behind resilience, and kind of work out what the calculations and everything are. So Kannan, should I just kind of start working through the...
Yeah, let's. You could share the deck and we could get started.
Yeah, let's get started. Yeah. So it's all about. Can you see that? Okay, just checking.
No, I don't yet see the share screen. Is it just me? No, I don't think it's. Maybe there's some delay.
It says it. It says it's sharing.
Oh, yeah, there you
go. It just took a little bit of a delay. Coming over from the UK, maybe. Yeah, so it's all about the mathematics behind resilience, and I guess we just wanted to start with a little bit of a kind of perspective around, does resilience actually really matter? And specifically, this is within the context of scaling architectures. If you're scaling clusters, horizontally scaling clusters, how does that impact resilience and high availability? So we're going to look at two particular scaling architectures, one of which is the Yugabyte architecture, and one of which is like an alternative approach to horizontal scaling, and then look at how that scaling architecture either, helps or hinders high availability and resilience. We are going to get into a little bit of maths. So we're going to look at a little bit of probability theory and apply that to the two different architectures, and then draw some conclusions. So I guess the first thing is, does resilience actually matter? Or I guess more importantly, more thoughtfully, how much does it matter? And I picked up a quote here from Mark Watson. He's the CTO of ComplyAdvantage, one of our customers, a fintech that focuses on anti-money laundering, anti-financial crime. And what he's on record as saying, he was actually doing, this was actually a ComplyAdvantage webinar, nothing to do with us. And he was talking about how any kind of outage across their infrastructure, across their solution, has significant impact on their customers. So their customers are running 7x24 systems, kind of monitoring transactions, looking at politically exposed individuals. Any kind of outage has significant impact monetarily on their customers. And then the relationship that ComplyAdvantage has with their customers is there's a knock-on kind of penalty and other kind of financial impact on them. So it's really important that solutions are resilient. But in the modern world, obviously scale is really important too. So just nipping back to Mark at Comply Advantage, this was a conversation I was having with him actually. He said that he was looking at their infrastructure and they're processing 1 billion requests per day. That's approximately 11,000 queries per second on average. So obviously, as people that are familiar with this channel will know, that calls upon the need for some kind of scaling, ideally horizontally scaling architecture. So that's where these two worlds kind of collide in some ways. You've got a requirement to scale the architecture, make it in quotes more complicated, but there's more moving parts, there's more servers, there's more things going on in order to handle the scale. But at the same time, you want it to be ultra resilient. So what we're going to do is look at two particular architectures. The one on the left, people will recognize as in some ways a kind of little bit fairly simple, kind of almost naive approach to scaling, where you just shard your database at the application level. You break it up. You put part of your database on one instance of Postgres, and then other parts of the database on other instances of Postgres. So the example I've given here is maybe your overall customers are split. Those between A and E are on the first one, all the way up to those between W and Z on the other one. There's lots of other ways that you can segment the data, but that's essentially what you're doing. You're breaking the application and the database up, and you're creating multiple stacks. Quite in contrast with Yugabyte and distributed SQL, where you have a single strongly consistent database or cluster, and then all the nodes collaborate together in order to serve that overall kind of unified database. So quite a different approach. If you look a little, if you think about those two architectures, and look behind the scenes, then let's think about the potential failure scenarios. So in both of these cases, the individual servers are running probably on VMs, sitting inside a public cloud. And if you look up the availability objective of those underlying VMs, for example, GCP quotes it at 99.9% uptime, so 0.99. I've actually just got the page here from the GCP service level objective and pages, and you can see that with a compute GCE compute node, it's saying that it's kind of guaranteeing, or the objective is a 99.9% uptime. So that's the kind of base availability, the kind of the compute engine that all these architectures are working on. On the left-hand side, the application sharding model, all of those nodes are independent. They've all got their own kind of 99.9% uptime kind of objective associated with them. The key thing about application sharding is to have the entire database available. Obviously, you need all of those nodes to be available, all 6 of them in the particular example that we've got, and that's kind of a critical piece of information that we should remember. In the distributed SQL example, and we're starting off with RF3, replication factor 3 here. Again, the probability of each node being available is the same. We're running on the same VMs. The availability profile of each node is also independent of each other. So the nodes, each of the nodes have the 0.999 availability. But crucially, the data is replicated across the entire cluster and then organized, as people on this channel know, around these kind of quorum groups. And those groups are spread across the 6-node cluster evenly. And what that means is that if any node is lost, only one copy of the data is impacted and the cluster continues to operate. If two or more nodes are lost, then the cluster is impacted. I put a note here on the bottom left-hand side that also notes that if two nodes fail in the same availability zone, Yugabyte is thoughtful and careful about how it organizes the data. In this particular situation, you could actually suffer two nodes going down. So you can suffer a full AZ failure, two nodes go down in a 6-node architecture, and that's okay. I haven't added that level of complexity into the mathematics. I could have done. It actually increases the uptime, it improves matters, but I just haven't included it in this presentation. It is included in the blog post if people are interested and want to have a look at it. So pause that thought for a minute. Application sharding, you need all 6 nodes to be up. Distributed SQL, we can suffer one node being down and the system keeps working. So first of all, let's introduce a little bit of probability theory. So as I'm sure most people know, in maths, if two events are independent, then the probability of both of those events happening together is, you multiply those probabilities together. So the probability of A and B is calculated as the probability of A times the probability of B. To bring it all to life a little bit, I've got the example of just rolling a bunch of dice. So the probability of throwing a 1 is obviously 1 in 6. There's 5 values that you could have thrown which aren't a 1, one value that is a 1. So it's a 1 in 6 chance that you're throwing a dice. If you throw 2 dice together, then the probability of throwing 2 6s at the same time, you multiply them together. So it's a 6 squared, and the probability of throwing all 6 6s is the rather tiny 1/6 to the power of 6, which gives you this 0.402. So it's a kind of unlikely scenario, which kind of matches with real life. If you bring that concept and that approach to probability theory back to our 6-node cluster, then as we said at the beginning, in order for the entire cluster to be up, all 6 nodes need to be available. All 6 nodes need to be up. We calculated, or we were told by GCP, that the probability of a single node being available or being up is 0.999. So therefore, the probability of all 6 nodes being available is 0.999 to the power of 6, which is 0.994, i.e. 99.4%. So what we've just done there is calculate the service level objective of a 6-node sharded application sharded database. The service level objective of that is 99.4%, commonly referred to as 2 nines, maybe 295 if you were generous. And I guess the key thing to note about that is partly due to the way application sharding works. The service level objective of a 6-node database is actually quite significantly lower than the SLO of the individual VMs that it's running on. And that's kind of an interesting point to note. Things get worse from a reliability and high availability perspective with application sharding.
And Chris, I was just on the side, trying what would happen if it was an application sharded cluster with 12 nodes. And as you can imagine, like now all 12 nodes need to be up and running for the service to be available. And this number drops to about 98.8.
Yes.
Yeah.
Yes. Yeah. It's cumulative, or actually multiplicative, isn't it?
Yeah.
So it kind of gets worse and worse and worse as a customer would scale their application sharded database out across more and more nodes. Then you end up with worse and worse reliability profile. So yeah, it's kind of interesting thought, isn't it? it's the maths that shows that it sort of gets worse as these things expand.
Yeah.
So let's come back to a bit more probability theory, and this probability theory is called binomial distribution. It's all to do with this concept of what's called a Bernoulli trial, where you're testing something and you've got two potential outcomes. In the sort of database world that we're talking about, those two outcomes is that you're looking at a server and it's either up or it's not up. They're the two potential outcomes. Just starting in the dice throwing world for a minute, what I want to do is calculate the probability of throwing. Actually, I'm throwing two ones here. What's the probability of throwing two ones at the same time, exactly two ones at the same time, if I'm rolling three dice? And the probability theory starts to get a little bit more complicated, not too much. So as we know, the probability of throwing a one is 1/6. The probability of not throwing a one, i.e. throwing some number between 2 and 6, is 5/6. Yeah, there's five numbers on the dice that isn't a 1. 5/6 equals 0.83. So the probability of throwing exactly, a 1 followed by not a 1 followed by another 1 is, multiply those two things together, you get your 2.3%. That's one way of throwing a couple of ones. There's other ways of throwing a couple of ones as well. So the first way is 1, not a 1, 1. I might throw not a 1 first, followed by two ones. I might throw two ones first, followed by not a 1. And that's the three different ways that I can throw exactly two ones when I'm rolling some dice. So what the probability theory tells us is the overall probability of rolling a pair of ones is 3 times that number we calculated in the first place, i.e. 6.9%. So now what we want to do, so that's the way of calculating in a system, calculating if there's exactly two binary occurrences of something in a set. So how do we apply that to our distributed SQL cluster? Well, first of all, I've just written down here the generic formula for calculating that binomial distribution. So what we're looking at here is the probability of k occurrences of n trials, and the calculation here is it's easy to Google this and look this up, but it's n k combinations of k and n. In Britain we use the term combinations. I think in America you use the term choices. So choose k out of n, and then it's the probability to the power k, 1 minus the probability to the power of n minus k. We can kind of gloss over this maths because it's easily Googleable. What I want to do is apply that to the 6-node distributed cluster. So what we know, because we looked at it in an earlier slide, is the probability of the cluster being fully up is the probability that exactly 6 nodes are available, plus the probability of exactly 5 nodes are available, i.e. 1 node could be down or 0 nodes could be down, and the cluster will continue to operate.
And just to remind our viewers, and that's because the replication factor is 3, and in a quorum protocol, we can in general tolerate one of the one of the members going down. So that's just a reminder. Yeah, thank you.
Yes. Yeah. Perfect. Yes, exactly. So applying that formula up that we just looked at, the probability of 6 nodes are up is there's 6 combinations in 6. Well, that's 1. Because all 6 of the servers are in the same state, and then we've got it's the same calculation as with the other clusters. So all 6 nodes are up, 0.999 to the power 6. That's the 99.4% that we saw earlier. But then crucially, we also are okay if only 5 nodes are up. So that's combinations of 5 in 6 or 6 choose 5 in American lingo. 6 choose 5 is actually, if you calculate it, is 6. And then you've got the 0.99 to the power 5 multiplied by 1 minus 0.999. And that gives you an additional 0.0005 probability. Add these two things together, and we've ended up with 99.998% uptime. So interestingly, the 6-node RF3 distributed SQL cluster has a service level of objective of 99.998%. So 4 nines uptime, almost 5 nines uptime, which is significantly and notably higher than the service level objective of the underlying VMs. And I think that's the kind of interesting thing about doing these calculations, is that the application sharded cluster deteriorates in terms of reliability, and the distributed cluster improves in terms of reliability.
And just to call out, and there's a related question here, just in this slide, the lowercase p is essentially the single instance failure probability, which is the 99.9 number that we started with. So one of the questions was, does that probability apply to nodes within a single region only? And this question is about the lowercase p, right? Does it apply to nodes only within a single region, or does it apply to nodes across regions or across clouds?
Yeah. So there's some extra complexity when you start to think about an overall system. But yeah, so within this context, Google and Amazon and Azure are guaranteeing or giving a service level objective of 0.999 at the individual VM level, no matter where those VMs are spread, whether in a single region or multiple region. The beauty of the distributed SQL architecture is that we extend the kind of resilience such that it can be applied across whatever failure zone you want to deploy across. So whether it's across availability zones or availability regions. So calculating the resilience of the cluster at this node level extends across zones or regions or clouds, come to that. I think the extra level of complexity that one would want to introduce is, if you're spreading across regions, you'd need to introduce what's the probability of a network failure between those regions. And so you can kind of extend the calculations to include that if you want to.
Yeah, so just to make a few points, again, maybe re-emphasize, the lowercase p number of 99.9 is almost independent of whether the node is in zone A or zone B or region. It is what the cloud provider is guaranteeing in some sense. But and Chris alluded to this earlier, when in calculating the overall probability of uptime, the number might actually be slightly higher than the 99.998 that you see in this example, because the one additional case that is okay is the probability of 2 nodes being down, as long as they are in the same zone, right? So actually these numbers get better, and Chris mentioned that in the earlier slide, and his blog actually covers that case also.
Yes, yeah. And actually that extra bit of availability does actually notch it up to 5 nines, interestingly. So you just creep over that kind of 5 nines target. Just looking at the time, so I'm going to whiz on to RF5. As you remember, what I was saying was the customer we were talking to was saying, so what's the impact of RF5? Well, RF5, as everybody knows, we need quorums. That means we need three out of the 5 nodes to be available. That means we can suffer 2 failures. So mapping that forward, that means that in the middle of the screen here, we're saying that the cluster is available if exactly 10 nodes are up, or exactly 9 nodes are up, or exactly 8 nodes are up. Notwithstanding the comment Kannan just made about multiple failures within an availability zone. So we're kind of setting that aside. So whizzing through the maths again, exactly 10 nodes are up. Footnote: the reason I've moved to 10 nodes rather than 6 is we've got RF5. You typically run that on 5 availability zones in order to have an even number of nodes on each zone. I've chosen 5 times 2, which gives you the 10. So the probability of all 10 nodes being up is this p, 0.999 to the power 10. That gives you 0.99 of availability. The probability of 9 is combinations of 9 and 10 calculation. That gives you an extra 0.099 of availability. And then the probability of exactly 8 nodes being up adds in an additional 0.4044. If you add that lot together, the probability is 99.498%. A fraction short of 7 nines, so kind of what you could call 6 nines 8 availability. So again, the approach of quorum-based distributed architecture, as the cluster gets wider and bigger, and as you increase up to RF5, you're actually improving or increasing the availability. And 99.498% again is significantly higher than the RF3 setup, and is also very significantly higher than the underlying service level objective of the individual VM. So in summary, we've got the way things work when you calculate them. An individual node has a service level objective of 3 nines. 6 node application level sharding deteriorates matters. You're down to 2 nines. 6 node RF3 increases matters significantly. You're up to 4 nines 8. And if you really want to achieve ultra high resilience, being able to suffer 2 contemporaneous failures, which could be a planned, an unplanned failure while you're doing planned maintenance, that kind of scenario, then you're up to 6 nines, almost 7 nines availability. I wanted to just finish with a quote that I told Mark that we were doing this presentation, CTO Comply Advantage, and he said his retort to me was that the jump from 2 nines to 6 nines availability is not just an academic exercise. The maths is really interesting, but it's not just an academic exercise. It actually implies millions in risk reduction. And really, resilience and high availability is all about risk reduction. That's what people are kind of architecting to protect. It's a bit conscious of time, Kannan. Any further?
Yeah, I just wanted to give some. If you could go to the one slide before, I wanted to give a little bit of insight into what this might translate it in terms of actual time. Like when we say the 6-level application sharded cluster is 99.4% available, it's kind of like one way to think it's like roughly like an upper bound, right? And when the cloud provider is saying that an instance has 99.9% availability, it doesn't mean that the remaining 0.1% of the time it's guaranteed to be down, but it just sort of like gives you an upper bound. But if we plug in these numbers into, say, a monthly time frame, then what I wanted to give people the intuition is this 99.4% row in a monthly time frame translates to about 4 hours and 22 minutes. So there could be up to like a 4-hour and 22-minute outage is sort of like what the promise is of this architecture, right?
Yeah.
Whereas if you go one row down where you go to 99.998%, and if you plug that in as what it means in real time for a month, that's 53 seconds. So basically on one side you have like 4 hours and something, and the other side you have 53 seconds. So it may not be so intuitive from these percentages, but the difference is dramatic, right? And so yeah. It's I don't know if you had any other slides, but did you have any other slides, Chris?
No, that's all of the slides. And I think just in summary, I think it's actually a really useful exercise to try to put a quantitative perspective on availability, and sometimes it's a little bit difficult to relate to risk and how available things are. We're all quite good at having a qualitative perspective. It's highly available, it's highly resilient, but I think it's really useful to be able to apply some kind of numbers and mathematics and percentages, these things, to really quantify it. And then, as you just mentioned, that gives you quite a stark contrast on the different architectures and the impact on their resilience, and therefore the impact on risk reduction, which is what the Mark Watson quote is about there. Ultimately, the CTOs, CIOs of organizations are all about assessing risk, and this really helps with that, I think.
Absolutely. And I think there was a funny question / comment saying, at what replication factor will we get a service level availability of 100%? So, but I would rather say that, while all of these percentages are talking sort of about the uptime promise of the backend system, this to fully realize it, there is a lot of best practices that the application must follow, in terms of like retrying connections. Because yes, the database might be available, but if a socket timeout is 20 seconds, then some set of requests will see that hiccup, right? Like, so, and how quickly you fail over to another node. So there's a lot of like best practices around um, this that you still need to follow to get the maximum uptime, not just for the database, but for your entire application. But with that, maybe it's a good time to close this episode of the Tech Talk. I wanted to thank everybody for joining us. See you again on another episode of YFTT. And I'd like to hand over to Chris for closing comments as well.
Yeah, thanks very much. Really appreciate it, and speak to you next time. Thank you.
Thank you all.